All right, so let's dive deeper into physical stability. When we think about physical stability in powders, there's really three major factors that we want to consider: moisture, temperature, and time. So I'll let you kind of dive into these and add on as needed.
Yeah, for moisture, basically, if we have more availability of moisture, we're going to have more processes to change, right? More structure to change. When you were talking about the DDI, my first thought was looking at that in terms of like a spray-dried milk powder, where we're going from a glassy state to a rubbery state. Now, if we did a different, more traditional style of isotherm, you actually miss that transition because it's essentially jumps over it, right? You normally kind of hold things at certain humidities and see what happens. But in the DDI, it's the real-time process, and you can actually see these transitions happening. So this is what I specifically am meaning when I'm talking about using the isotherms to be able to see your real-time data and when those critical points start to happen. So moisture is a major impact for those processes because water tends to really speed things up. And so it can be a solvent, it can be a reactant, and it can actually even be a buffer into the chemical reactions. And sometimes the roles change as the process goes along or as more moisture is added to that process, and then you can see different reaction rates actually change. So besides moisture, we can also want to look at temperature. And we do have a graphic that we like to show because it's a really great way to express how that critical point that we've been mentioning will change as we're adding heat or temperature, increasing in temperature to a product. And what happens, and it does make sense when you think about it, is that change happens faster. You're adding energy into the system, and that system, it's flowing faster. So you'll get these changes happen at what would be lower water activities or faster in that process. The last thing is time. If you give a process enough time, it's going to change. So even if you could hold the other things to static, temperature and moisture, if you gave it enough time, it would happen. And I was just thinking the other day about this example. If you've got really old glass windows, and if you were to measure the top and the bottom of very old glass windows, you would know that the bottom is thicker than the top, and that's because they've had a long time to flow. So that's kind of this idea of if you give something a process long enough, it's going to come to completion. All three of those factors will play into physical stability.
And I think it's also important to note, depending on your question, there are different methods or different types of isotherms that you can use. So going back to the dynamic dew point isotherm, you can use this to find that critical point and understand exactly at what water activity or at what relative humidity and temperature combination will cause that effect. And then once you know where that critical point is, then you can also do a DVS test, a dynamic vapor sorption test, to ask the question about time. So going back to your window example, how long is it going to take to actually reach this critical point under a certain condition? And, we have a solution. We have our vapor sorption analyzer that allows you to do both of these methods, which is really unique and really the only instrument capable of doing both of those. So if you have a problem with physical stability, having access to both those types of tests can be really effective. Now let's move a little into your spice mixing project. What was this project? What was the goal of it? And what did you learn from it?
Right. So as we know, moisture will move because we have differences in water activity. So the question is, how much does it move? Can we predict that, and how accurate is the prediction? So we do have a tool. There are definitely equations out there that try to model that interaction between products. And so what we did for our project was essentially that. I think we had 6 different blends. Some spices, we did a maltodextrin and sorbitol, cornstarch and onion salt, and then some spices, sage, oregano, and cumin. We put them together. First, we forced all of them to have a very specific water activity. So and then we also ran isotherms on all of those ingredients because that is a major factor, not just the starting water activity or a mass ratio in the blend, but what is the characteristics of that isotherm, of how does it behave in the presence of moisture. So we want to know how they take up or don't, or however that might be. We need to know what that information is for that product so we can do a good predictive model. So we did this, and then we mixed them together in known mass ratios. And then we measured to see exactly what the water activity was after we gave them time to equilibrate. And then we also did the prediction. And they were very good. Basically, I'm showing the combinations that we did. The top one there, cornstarch and onion salt. We mixed 1.5 grams of cornstarch, and it started at a water activity of 0.435. And the onion salt, we did it as a gram, but we had it at a lower water activity. So you'll see there that it started at 0.35 water activity. And then we blended this, and our blend actual water activity was 0.429. And when we ran the predicted model that took the isotherms into account, the initial mass, and the initial water activities, we actually predicted that the final water activity would be 0.431. So extremely close. These worked really well. They have really fine particle sizes, actually, so they have a lot of contact, so you're going to get a quicker equilibration. And so that wasn't too much of a surprise. But it was nice that it worked so well. And you can see with some of our other examples that we ran very well. We also did maltodextrin and sorbitol. We varied the amounts. We varied where they started. One was higher than the other one, and then we swapped it. We kind of tried to do various combinations to just test it out a little bit. And then we also did the spices at the bottom, the sage, cumin, and oregano. And those worked quite well. Our worst case scenario in the setup that we did was the very last example. And maybe I shouldn't say that, but the scientist in me says I need to. And you will see that our predicted was 0.35 water activity, where our actual was 0.395. So it was about 0.05 lower. And I just kind of wanted to talk a little bit about how this works and then the comparisons we did. So you'll see here all of the isotherms for the sage, the cumin, the oregano, a combined model, so where we put those all together. And I also wanted to show where we started. This is where we started with all of the ingredients, where the initial water activity, what the initial moisture content was based off of the isotherm and the mass ratios. And once we put it all in there, you can see there that we got a final water activity of 0.349. Now, for this, what's important is we're doing this mathematically. So we want to make sure that we have a good representation, a good mathematical equation and coefficients for each of our ingredients. Once we got that, we got our prediction. It was pretty close. I was pretty happy with that. I think they're just, particle size, perhaps with the spices maybe not having as good a contact. It's possible that once we let them be together longer, we might have had a different, slightly different result. But I was very pleased with the result that we got. I also wanted to take this and look at it the other way. So we modeled the isotherm, as I'm showing here in the red trace, but then I wanted to also compare that with the real isotherm, because after we mixed this blend, we actually ran an isotherm on it to see what we could do. And from there, you can see the differences between the actual isotherm and the modeled isotherm, and they match up very, very well, and especially in the area of interest that we're looking at. So if we're looking around, for spices, maybe 0.2 to 0.4, it's generally kind of where they live in water activity range. You'll notice we have a really nice fit. So I feel very, very good about our data in our study. And this was, like I said, is the worst case that we had. The rest of them actually had much better results. So
I just kind of want to take a step back and think about the real world application of this. I talk to scientists all the time who are under a lot of pressure to get new products out as fast as they can. And if you use this type of modeling for a dry ingredient mix, this is a really fast way to get lots of insights about that final product before you even make it. So it does take maybe a little time to build up a library and have isotherms for each ingredient. But once you do that, then you can sit at your computer and very quickly understand what the equilibrium water activity will be. And with our new program in the moisture analysis toolkit that comes with our vapor sorption analyzer, the toolkit software does all of the work for you. You mentioned those equations, and there are equations in the background, but instead of having to build your own spreadsheet or do this all yourself, all of that labor is being done for you, and it makes it really easy to know what the equilibrium water activity will be. And now you can also get the coefficients for that model that you mentioned. And using those coefficients, you can start to ask questions about, what is the predicted shelf life, or how long will it take to reach a critical water activity, or maybe what type of packaging should I use? And so there's a lot that you can do if you take the time to look at these isotherms and understand exactly, how can I use this data to answer lots of different questions. So I just wanted to point that out, that, the graphs that you're showing do come from the moisture analysis toolkit software. And this is something that a lot of our clients, whether they're making nutritional supplements or, we work with some of the largest spice producers in the country, they're using these equations and using these tools to speed up their production.
Right.
So I just wanted to make sure to point that out.
Yeah, that's a really good point. And I also wanted to add that once you have the isotherms, I can rerun this prediction over and over. I can change any part of it and rerun it in just moments. As an example, I could change the mass ratio if we find that we don't particularly like this blend, or it has we don't like the flowability of it, or something, or maybe the flavor isn't good. Maybe it's got too much cumin in it or something. You could adjust that recipe, right? And you can just do it in the software. Or let's say, as an example, we've talked in prior webinars about the seasonality, how that can change your incoming ingredient water activity. Tends to be higher in the summer and lower in the winter. And so, it's important to monitor what you're getting when it arrives, so you don't get a surprise and moisture coming into your product that you didn't anticipate or want. That's something you could change here. You could change the initial water activity of any of these products and then just rerun the prediction. So once you get that information, you can do a lot with manipulating it.